Hello everyone, welcome to the sixth episode of Math and Beyond and this podcast. Today we're going to talk with Giovanni Maria Tomaselli about the Lambda CDM model, the cosmological model, and ultimately also about black holes. But I have already done an episode about black holes, so we will be tackling a different question than what I have previously covered with I believe it was Sheresh, with whom I talked about black holes. So yeah, now we're going to wait for Giovanni, and I will see you shortly. Hi, Giovanni.
Hi.
Hi, how are you?
Good, thanks. I'm good.
Yes, everything is fine. Where are you?
Sorry?
Where are you at the moment?
In the main, like very close to my office, in the main building of UVA at Science Park.
Science Park, okay. Yes.
I don't use my headphones if it's fine.
No, it's okay. It's okay. Yeah, I hear you perfectly. Yeah, great. Okay, so I gave a small introduction about the topic of our discussion of today. So the Lambda CDM model and ultimately black holes. And I was saying Giovanni, Gimmy, for well known as Gimmy. You studied the theoretical physics in Italy, both as a bachelor degree and master degree, right? And yes, and now you're doing at the University of Amsterdam your PhD in cosmology.
Yes, at Grappa, I would say, not just cosmology. Yeah.
Okay. So yeah, so I think I believe we can jump into it, and I will ask you very briefly. I just said I just say an acronym. I just said a name, but what is Lambda CDM? What is Lambda and CDM?
Yes. So it's funny because this name. So this is an acronym, as you said. And it's the name that we give to the so-called concordance cosmological model. And it's funny because the two components of the name, Lambda and CDM, are two things we are very confused about. So Lambda and CDM, so Lambda stands for the cosmological constant, which is usually denoted by the capital Greek letter lambda in Einstein's field equations. And CDM stands for cold dark matter. Now we have a cosmological model we'll talk about in detail today, which has many components in it. And the two most mysterious ones are also the two most important ones. And they are these two. So the cosmological constant, also known as dark energy, and the cold dark matter. So if you want, we can briefly say what are the characteristics of these two different things.
Yes, absolutely.
Okay, so let's start with the dark matter. So when we look at the universe with our eyes or with a telescope, we are sensitive to electromagnetic radiation. This usually comes from, for example, stars or other events in the universe that release light. However, there is a lot of matter in the universe that is not emitting light, so we have no way to see it with a telescope, say. This can happen with ordinary matter as well, so matter made of protons, neutrons, and electrons. But a very long list of observations in independent measurements suggests that the amount of matter that does not emit light in the universe is way more than what should be expected from the standard model only. So from the particles we know from experiments we did on Earth. And by way more, I mean that about the ratio is like 15% to 85%, something like that.
So yeah, just for clarity, you mean 85% of hypothesized dark matter in the universe and 15% of what we know as baryonic matter, right? So deriving from elementary particles.
Yes, roughly.
Okay.
Now, dark matter has a long history that traces back to the 1930s with Zwicky. But then the evidence for the existence of this extra matter in the universe became accepted in the community, I think, around the 70s or 80s. So a bit more recently, although not too recently. And we know that this mysterious matter should be in the universe for a number of reasons. Some of the most common explanations are the rotational curves of galaxies. Like we looked at galaxies, we compute what should be the velocities of stars orbiting the galactic center based on the mass we see in the galactic center. And we find that the stars are orbiting as if there was much more mass in the galaxy than we see, okay? So this is one common evidence, and there are many more. There are cosmological evidence and so on. So we just call this component of the universe called dark matter. We don't know what the fundamental particles of this matter are, if it's made of fundamental particles. And yeah, that's basically it. We also we know many of its properties though. We know, for example, that it's matter in the sense that it behaves cosmologically as ordinary matter, not like radiation. So it's not like light, and it's not like dark energy. We'll talk about in a minute. And by behaves, I mean that its energy density changes with time the same way the energy density of ordinary matter changes with time, okay? So they behave in the same way in the Friedman equations that determine the evolution of the universe. And we also know other properties. Of course, it shouldn't emit light, or at least not too much. And it's cold. What do we mean by cold dark matter? We mean that it should not, its particles should not be too fast. You know, in physics, the temperature is really intimately related to the temperature of a system. The faster the velocity of the particles, the higher the temperature of the system. So cold means that the particles are moving slowly, and by slowly we mean non-relativistically. Okay, at the time of
what do you mean? What do you mean precisely saying adding the part non-relativistically?
So if you have well, any particle can move from a velocity of 0 to the speed of light. Non-relativistically means that the velocity of the particle is much smaller compared to the speed of light.
Okay. Okay.
Otherwise, if it's very close to the speed of light, we say that the particle is ultra-relativistic, or if it's comparable to the speed of light somewhat, we say that it's just relativistic.
Okay.
By relativistic, we don't need to apply relativistic corrections due to the finiteness of the speed of light.
Okay. Okay, I understand. Sorry. Yeah.
Okay, yeah, that's the outline of cold dark matter. We
Okay.
can see later. And then the other main component is.
Can I ask you one very quick thing? So basically, going through the internet and reading a bit about the dark matter, there is, let's say, I've at least glanced that there is one, let's say, special candidate, which is called Whims, weakly interacting
massive particles.
Massive particles, yes. Can you give a very brief explanation of what we believe Whims are, which are our candidates, let's say, for dark matter?
Well, so because we don't have an explanation for the fundamental nature of dark matter, people have proposed many possible solutions. One of these is Whims, but there are many others. Whims, though, historically have been probably the most important proposed solution to the dark matter problem. I'll explain in a minute in detail what they are. But I also want to mention that they fell like the shining period of Whims ended a few years ago for many reasons. So now people are considering much more alternative hypotheses. So the idea behind Whims is that you could have particles that interact with the standard model only via the weak force. You know, there are only 4 fundamental forces in nature we know: gravity, the weak force, electromagnetism, and the strong force. And I'd say them in the increasing order of strength. So the weak force is quite weak, as the name says. And it's possible, and also predicted by some theories that go beyond the standard model, that there exists some particles that interact very feebly with the standard model. So it's very hard to see them because they, you know, if you want to detect a particle, you have to make the particle interact with your experiment. If the particle never interacts with your experiment, you're never detecting the particle. And if particles only interact with the weak force, then it's very hard to see them in experiments. It's possible, but very hard. And Whims is a generic name that people gave to these candidates that popped out of many theories that go beyond the standard model, in particular supersymmetric theories.
Okay. So you were picking on lambda. We explained the CDM called dark matter. What is the remaining part of the acronym lambda?
Yes, the lambda, as I said, is the cosmological constant. And well, if we are confused about cold dark matter, we are extra confused about the cosmological constant. There's also an interesting historical story, let's say, of lambda. But let's say that if in the universe you only had things like matter, be it ordinary matter or dark matter, and radiation, the expansion of the universe should decelerate. So the universe can continue to expand, but at a slower and slower rate over time. Then in 1998, 2 independent teams that eventually won the Nobel Prize for this discovery made some observations. They observed supernovae of type 1a and discovered that the universe is actually accelerating its expansion. And this was a huge surprise for the community because it requires something that goes beyond ordinary matter and even dark matter, something that behaves in a completely different way. Now, the way exactly the universe expands can be measured more precisely, and this has been done recently with especially the Planck collaboration. And the best, let's say, I don't want to call it an explanation, but the best, like the simplest model we have for that is the addition in the energy content of the universe of a mysterious component, which we call lambda, that basically is energy associated to the space itself. Like when the space expands, it creates more of dark energy. And it also have negative pressure. If you think about it, this does not happen with ordinary matter. For example, if you have a galaxy, there are some protons in the galaxy. If the space expands, the number of protons remains the same. So they don't multiply with the expansion of the universe. Instead, this does happen with lambda. Now, we have truly no idea what this is. However, we do know something in physics, from particle physics, that behaves in exactly the same way. And this would be naively the easiest interpretation, and that is the vacuum energy of quantum fields. So basically in quantum mechanics, even the vacuum, so the absence of any particle, has a non-zero energy. And this is due, if you want, to the indetermination principle of Heisenberg. Okay. It's also called the zero-point energy. Maybe it's more well known with this name in popular science. So if you compute how the vacuum energy behaves, well, it's exactly the same thing as lambda. Like it behaves in exactly the same way. But there's one problem. Physicists have tried to estimate how large the vacuum energy of quantum fields is. Just did an estimate. We can't compute it exactly unless we have some theory of particle physics that holds up to arbitrarily high energies. But we can do an estimate. And that estimate does not match observations. But not by a little. There are 120 orders of magnitude of difference. This has been quoted as the worst prediction in the history of theoretical physics. So surely what we see is not the energy of the vacuum of quantum fields, or at least not what one naively expects. So yeah, that's basically where we stand. People have proposed a huge number of possible hypotheses, but so far lambda is just a parameter, just a number that quantifies this energy associated to the space, and we call it dark energy. That's it.
Okay, you added the, if I can ask a further clarification, before you added the negative pressure.
Yes.
Yes, can you elaborate very quickly on negative pressure? Because I understood well the first part and I got stuck in a negative pressure. Why is that the case?
Yeah, I understand it's quite counterintuitive. So for example, gravity is only attractive usually. If you take two masses, they attract each other. And you see, in the same holds roughly if you take a fluid made of ordinary matter. If you have two regions of the fluid, they attract each other. Yeah. Negative pressure is a way of saying that dark energy is like repulsive gravity in some sense. So the more you have it, the less gravitational attraction you have it in some sense, or even like the contribution of dark energy is like a negative gravitational attraction. So it pushes things apart instead of together. A more technical way to explain it is to, so there's a quantity that enters the Einstein fields equations on the right-hand side. It's called T mu nu. That's the so-called energy momentum tensor or stress tensor. And in that object, there is something, there are quantities like the energy density of the fluid, the momentum density of the fluid, the pressure of the fluid, and so on. And the parts related to the pressure have a different sign between ordinary matter and the cosmological constant. And in particular, they are negative for the cosmological constant.
Okay. Okay, I see. Thanks. Yeah, so I would like to ask you, how does our model, this model explains what we see in the bigger picture? So how does Lambda CDN model explains the large-scale structure of the universe, and where do dark energy and dark matter come into the picture?
Okay, so the large-scale structure of the universe is something that basically can be, in principle, computed out of the initial state. So the Lambda CDM model postulates that the universe at a very early time of its history was in a state of high temperature, high density, that subsequently evolved by expanding, so reducing temperature and density. Initially, the universe was nearly homogeneous. So there were, here you see many dishomogeneities. There is the Earth, and then there's vacuum, and then there's the Sun, and there's the Milky Way, and then there's vacuum again. So matter is concentrated in many places. But initially, the universe was very smooth. There were very little differences between different parts of the universe. Then, as the universe expanded, these very tiny little differences became like larger and larger. So, for example, our galaxy, the Milky Way, originates from a very tiny perturbation in the density in the primordial plasma. The way the large-scale structure of the universe evolved from the primordial perturbation, so where galaxies are, what's the statistics of the voids and the filaments connecting galaxies and so on, is quite complicated, but can be understood easily at the perturbative level. So as long as perturbations are small, you can compute how dark matter perturbations evolve and how ordinary matter perturbations evolve. And what basically happens is that because dark matter does not interact electromagnetically, it collapses first. So dark matter is the first component of the universe that forms the first seeds of the galaxies. And then after that, ordinary matter basically falls into these potential wells and forms the seeds of what will become galaxies and so on. So this is the structure formation in short. What's hard about it is that when perturbations become very large, so when the universe starts to no longer looking smooth, you can't do analytical calculations as easily as before, and you need numerical simulations, and these are extremely hard to do. There is a very famous one, it's called the Millennium simulation, I think, which basically starts with the primordial state of the universe and then evolves these over several billion years and finds some web-like structure where the filaments are basically galaxies, the position of galaxies that resembles very much our universe. So the role of dark matter is basically to allow the formation of galaxies, because it prepares the gravitational potential well onto which ordinary matter falls to form galaxies. And dark energy instead only comes into play with the accelerated expansion of the universe. So it's not crucial for the formation of structures, but it's crucial for the late time evolution of the universe.
Okay. Yeah, I just searched. Yes, it is the Millennium Simulation project done by the Max Planck Society, I think. Okay. Yeah, I think it is very sort of a famous sort of picture that where they give they give a picture of the cosmic web. So they zoom out and everything that starts being, as you said, indeed homogeneous and basically all the same. Okay, but now you said at the very beginning, universe was very homogeneous. But now I want to make even a bigger leap, and I want to ask you, which is it is an event recognized by the Lambda CDN model, and that sometimes I believe people would find it hard to wrap their head around it. What was the Big Bang? Because the Lambda CDN model is basically built upon the Big Bang singularity, but what was it and why? What are some hypotheses?
One important thing to keep in mind is that the Big Bang theory does not say anything about the Big Bang itself. It says something about what came after it. So the Big Bang is just the name that we give to the fact that the universe was initially in a very high temperature and dense state. So if in the universe you only have the components we mentioned, so at very early times, the dark energy doesn't really count. So the important ones are radiation, so photons, basically, and the dark matter and ordinary matter. And you trace back the evolution of the universe, you hit at so-called a singularity, meaning that the universe, like the size of the universe, goes to zero at some point in the past. Now, we can't say anything about that point because our theories fail. Our theories cannot be applied to such a high curvature, such a high density universe, right? but immediately after it, that can be applied. So the Big Bang is just the name that we give to this idea that the universe began somehow its evolution in a very, in a state very close to this singularity. It's very similar to what you have in the center of black holes, where you have a region of infinite density, and we can no longer apply the Einstein field equations because they break, they don't work anymore there. It's the same thing with the Big Bang. So the Lambda CDM model only works after that, okay? And the Big Bang is not like an explosion that happened somewhere in space. It's just the overall structure of the universe that was once very small. So everything was close together. All the parts that are now in different galaxies, different parts of the universe were once very close to each other in this post-Big Bang state. Now, I have to say, though, that the existence of the singularity is not something well accepted at all. And in fact, the most probably the favorite theory of modern cosmologists is the cosmic inflation, that basically replaces this singularity with some other evolution of the universe, which is even which happens even before all the things we discussed so far. Okay.
God damn it, that we don't know what the Big Bang was. Okay. Yeah, so I wanted to ask you, related to the Big Bang, is the cosmic microwave background radiation. And can you briefly explain what that is and how, let's say, what is the significance of this picture in the Lambda CDM model?
Yes. So, okay, we said that the universe was once very dense. So dense and hot, so particles were moving very fast. So fast that, in fact, protons and electrons were not bound together. You know, in today's universe, you find atoms, where in the nucleus you have protons and nucleons, and electrons orbit around them. But in the primordial universe, electrons were moving so fast that they could not bind around nuclei. So there were no atoms, there were just free protons and electrons.
Soup, the cosmic soup.
The cosmic what?
The cosmic soup. I have heard it sometimes in some book.
Yeah, in more technical terms, that's called a plasma.
Okay.
And when you have a plasma, basically photons are not free to travel, because a photon that travels in a plasma interacts continuously with charged particles like electrons and protons, and scatters off electrons and protons. So it hits one electron, then it changes direction, hits another particle, and so on. While in our universe, if you send a photon, it basically travels straight, undisturbed, because atoms are neutral, so they don't interact strongly with light. However, the universe was cooling, so the density was decreasing, the velocity of particles was decreasing. And at some point, the electrons became slow enough to bind with the nuclei and form atoms. This is called the recombination. And this point in the history of the universe also corresponds to the moment where the universe became transparent. So photons finally could be free to stream through the no longer plasma, so the matter of the universe, which was now made of atoms, hydrogen atoms mainly. These photons, like a good part of these photons, are still free streaming in the universe today. And if we look at them with a telescope, we see them. That's the cosmic microwave background. One important thing to keep in mind, though, is that the frequency, or the energy, if you want, of these photons, at the recombination, so at the moment where the universe became transparent, was much higher than today. However, due to the expansion of the universe, like normal particles with the expansion of the universe slow down, while, yeah, they generally slow down, while photons lose energy. So they decrease in frequency. So they once were very high energetic photons. Now they are, as we say, redshifted. So the frequency is reduced, and we cannot see them with a normal telescope, but we need a microwave telescope. That's why it's called the cosmic microwave background. But so we are basically looking at the photons released by that plasma as soon as the plasma became transparent.
Okay, so we can say the first light of the universe.
Yes, and yes, in some sense. Although I think that this expression, this like first light of the universe, is also applied to something else, which is the birth of the first stars. Because after the combination, there was no star. The universe was still pretty homogeneous. Then density perturbations increased and formed galaxies and stars and so on. And then the first stars at some point started burning their nuclear fuel and released the first light in some sense of the universe. But that's light generated by stars. So just be careful with the light.
Okay, but now you said multiple times about the universe being homogeneous, and I think that these two problems that I want to ask you about, they may be related to it. So while reading a bit online, I've heard that there is this horizon problem related to cosmology, and there is also the problem of the flatness of the universe. Why are they a problem? Why do they represent a problem? And why are these two problems, as I've also read, are related to the theory of cosmological inflation that you mentioned before?
Yes. So let me first say that the universe was very nearly homogeneous, but not quite. And those extremely small differences are super important. But maybe we can discuss this later. So the horizon problem, the flatness problem. So we mentioned the Big Bang and the singularity before. But even though everything in the universe was very close once in the past, the universe also started to expand very rapidly. And in physics, there's a notion of being in causal contact between two events. So for example, if I am an observer here today and there is some alien on another planet, I can send a signal to the alien and the alien can answer me with another signal. It means that we are in causal contact, so we can exchange information. And this is possible because basically a signal that travels at the speed of light makes it in time to reach the planet where the alien is, and vice versa. If you calculate the same thing with the primordial universe, you actually find out that, say, if you look at the sky today and you pick different points in the sky, unless they are very close in the sky today, they have never been in causal contact in the past. So if you trace back their history, they could have not exchanged any particle, any signal, any information. So it's quite surprising that the universe is was very homogeneous, even though there was no mechanism to, make different parts of the universe communicate with each other. So if you look at the sky today, I think the area that was in causal contact is around, I think, half a degree, so very small. Different patches of this size were not in causal contact with each other. Now, this is true in the naive picture where you have, as I said, the Big Bang singularity at some point in the past. But people have proposed cosmic inflation that we mentioned, that basically replaces this singularity with another period of almost exponential expansion of the universe. And this has the effect of allowing causal contact between two parts of the universe. So they had been in causal contact during inflation. Then inflation made the universe expand so fast that the two patches of the universe ended up at very different places, so no longer in causal contact, but they once were in inflation. And I also want to say, you may say, well, what's the problem if two parts were never in causal contact? By the way, horizon means the horizon of information. So the horizon determined by the distance a light signal can travel. So that's why it's called the horizon problem. You may ask, I was saying, what's wrong with two parts not being in causal contact? Well, nothing is wrong, but it's disturbing that they had the same density, the same temperature, and the same everything. Like, why was the universe homogeneous on such a larger scale than the horizon scale? Like, you need some initial conditions. You need, like, God to say, I want the universe to have exactly the same initial conditions in different parts. That's disturbing. You would rather have a physical explanation for why they ended up with the same density, temperature, and so on. And being in causal contact provides this explanation. Okay, so it's a so-called fine-tuning problem. You can't fine-tune the initial conditions to have a very homogeneous universe. But from experience in physics, there's usually a deeper reason when two things are very similar or equal. Okay. So this is the horizon problem. The flatness problem is another thing. It's independent of it, but it's also solved by the cosmic inflation. So how can I say, the spatial slices of the universe, so let's say the spatial curvature of the universe could be positive, like the one of a sphere, zero, like the one of flat space, or negative, as if we lived in a hyperboloid. You could have these three different solutions to the equations of general relativity. And in principle, they are all valid. But if curvature is not zero, then in the equations that determine the evolution of the universe, you have this extra term associated to the curvature that grows with time. So now that we are at very late time in the universe, we should see a big contribution due to the curvature. Maybe curvature was very small initially, but then with time, this inevitably increases and should become much more important than dark matter and so on. But we don't see that. So either we have another fine-tuning problem where curvature, the initial condition for curvature was set to be extremely small at the start, so that it didn't have enough time to grow big enough today, or you introduce inflation, which, among other things, like during inflation, the contribution due to the curvature of the universe goes to zero, almost to zero. So it's a natural way to suppress the contribution of curvature to the energy budget of the universe.
Okay. What is your opinion on these two problems? Because they seem pretty radical problems, and when I think about them, I say, okay, this is pretty fucked up. Thinking about all these initial conditions of the universe being so nicely fine-tuned, and then cosmological inflation kicks in. Do you believe it is, let's say, it gives a reasonable explanation? Or it is, let's say, okay, this is a very bad term to say, but it is, let's say, just a proxy theory such that it works at the moment we believe it, but we have the sense, we have the feeling that it is not the inner reality.
Well, it's kind of both things. I personally think fine-tuning problems in physics are serious. I just say this from experience. Like, if you look at the history of physics, when you had fine-tuning, usually people found a deeper reason for that. I can't think of a situation where nature turned out to be extremely fine-tuned. Okay. With inflation, I would say it's just the easiest explanation. One of the minimal modifications we can do additions we can do to the Lambda CDM model to fix these problems all in once. There's also a third one that is fixed by cosmic inflation, by the way. That's the absence of magnetic monopoles. That being said, inflation doesn't have the status of accepted as every other thing in Lambda CDM. And there are also a few opposers of inflation. For example, one famous one is Roger Penrose. He doesn't think the theory of inflation makes sense.
What does he say? What does he propose?
I'm no expert of his ideas, but he has something called cyclic cosmology, where I don't want to say something wrong now, but he basically takes the end state of the universe and does something called a conformal transformation, and that corresponds to the start of another universe. But I don't know too many details on that. So let me say that inflation is not only, so maybe the thing that makes me like inflation the most is not quite the fact that it solves these three problems, so horizon, flatness, and the magnetic monopoles, but rather the fact that it made a prediction. So the small perturbations we talked about earlier, so the dishomogeneities of the universe, are actually predicted by inflation, in the sense that quantum fluctuations during inflation are stretched out on cosmological scales, and they become the seeds for the perturbations in the primordial plasma and then for the formation of galaxies. And inflation predicted, roughly, the so-called power spectrum of scalar perturbations. So the power spectrum is a quantity that tells you where the energy of these perturbations is, so more in long wavelength perturbations or in short wavelength perturbations. And inflation said, well, it should be nearly scale invariant, so energy should be nearly distributed evenly, but with just a very small modification. And so we have a parameter in the Lambda CDM model called the primordial tilt. It's called NS, which is, if it's very close to 1, then the spectrum is scale invariant. And it's been measured to be about 0.96. So very close to 1, but not 1, pretty much as expected from inflation. So that's probably the thing I like the most about inflation. Yes.
Okay. Hopefully we will be still alive when some discoveries with regards to inflation may pops out. But yeah, I would like to ask you to switch to another, let's say, question or matter that the Lambda CDN model explains, or at least I've read it explains, and it is the abundance of hydrogen, helium, and lithium in the universe.
Yes. So we explained already how atoms formed, right? You had protons and electrons and some neutrons, and at some point they recombined. But we didn't explain where the nuclei came from. So how many protons and neutrons you had, and how many protons alone, and for example, deuterium, so protons and nucleon together, or helium nuclei, which is 2 protons and 2 neutrons, and so on. So today we observe that about 25% of the mass of the universe is in helium, and 75% is in hydrogen. And the theory of Big Bang nucleosynthesis predicts these abundances with very high precision. So if you put in the parameters of the Lambda CDN model, so how much dark energy, how much baryonic matter you have and how much radiation you have and so on, you can predict how much helium compared to hydrogen you can see in the universe. And that's very close to what we see. I said 25% and 75%, that sums up to 100%. Actually, a very small fraction is in lithium and beryllium, I think. But they are very minor components that are nevertheless important in checking the predictions of Big Bang nucleosynthesis. And this nucleosynthesis process happened well before recombination. So because the energies involved in atomic physics are much smaller compared to the energy involved in nuclear physics. You know, the nucleus is smaller, and at shorter distances in physics correspond higher energies, and higher energies correspond to smaller and denser and hotter universe. So you first have Big Bang nucleosynthesis and then recombination.
Okay.
So yeah, I understand it's not easy to explain, but basically you can compute the rate at which nuclear reactions were happening in the universe. You can study many nuclear reactions, and you can compute the final amount of the final products, which are protons bound with the neutrons, and so on. To do this, you need information about the parameters in Lambda CDM. And yeah, the predictions are very good, match very well with the observations.
Okay. So yeah, now I will ask you about some, let's say, open problems with regards to this model at the end. Now I wanted to switch to your research area, which is black hole superradiance, right?
Yes.
Yeah. So I wanted to ask you briefly if you can explain. I've already, let's say, registered an episode on black holes and the most, let's say, classical aspect. Can you briefly explain, for those who do not know it, what is a black hole? And yes, what is a black hole in brief?
A black hole is some region of space-time from which light cannot escape.
Okay. That's it. Let's go to the next question.
And even technical definitions of black holes are just a formal way to say the same thing. You take the future infinity, and you compute all the events that could have reached that with a light signal. What's not in the set is the black hole, because light from there cannot go to infinity. That's it.
Okay. And what is the phenomenon of superradiance that you are studying and doing research?
Yeah. So usually when one thinks about black holes, one thinks that black holes can only, say, swallow stuff. They can eat planets, stars, and matter, and so on. And like, if light cannot escape from a black hole, surely nothing can. Well, this is half true, in that while, classically speaking, particles cannot escape a black hole, in that they cannot cross the event horizon in reverse, it is still possible to actually extract energy and angular momentum from a black hole. This is quite counterintuitive. I like to explain it with some classical analogy, but I'm not sure how insightful this is. Basically, the superradiance is intimately related to the dissipative nature of the event horizon. So you have some dissipation of energy, you can have superradiance. The example I have in mind is, you know, when you are at the airport and there are those tapirulon, you know, that help you in walking fast through long distances. So if you jump from standstill on the tapirulon, you get accelerated. Okay, you start moving with it. This is counterintuitive in that there is friction between your feet and the moving floor. So you are dissipating energy, but nevertheless, you gain energy by start moving. Well, that just happens because you're looking at the problem in the wrong reference frame. If you go in the reference frame where the tapirulon is still, then the friction is canceling your initial kinetic energy, okay? So it's all fine. With black holes, superradiance happens when black holes spin, okay? So if you look at things in the reference frame when black holes spin, it looks like the dissipation at the event horizon is giving away energy. But it's just because you're looking at things from the wrong perspective in some sense. It's just the dissipation of energy. Now, what do I mean by extracting energy? I mean something like send, for example, a wave on a black hole, so a light wave, and measure the same light wave after it has interacted with the black hole and find out it contains more energy after it interacts with the black hole. So the wave gains energy and the black hole loses energy and angular momentum. So that's the kind of extraction I mean. The first example of superradiance was proposed by Roger Penrose, and it's called the Penrose problem, Penrose process. And it's the same thing why you send a particle towards a black hole. The particle then decays in one piece that goes into the black hole and another piece that escapes. And if you arrange things properly and the black hole is spinning, basically the part that comes out can have more energy than the part you sent in initially. So you effectively extracted some energy from the black hole. So that's what superradiance is.
But how does it work? Okay, so firstly, I wanted to ask you one thing. What do you mean when you say extracting angular momentum?
Same thing with energy. You send some wave or particle that has angular momentum, so it's rotating with respect to the black hole. And after it interacts with the black hole, it rotates more.
Okay, so great. Okay, great. And then, and what do you how does a particle extract energy? How does it work?
So it's hard to answer, but let's take the Penrose process where you have particles, so it's easier to imagine. The point is, rotating black holes have a region very close to the event horizon called ergosphere. And in this region, you're not inside the black hole, so you can still escape from infinity to infinity. However, the rotation of the black hole is so strong that if you're in the ergosphere, you're forced to rotate with the black hole. Okay, so you're not inside the black hole, but almost. And the ergosphere has many different and weird properties, one of which is that particles can have negative energy inside it. So when Roger Penrose sends a particle and the particle splits into particles inside the ergosphere, one of the two is basically allowed to have negative energy. When this one goes into the black hole eats negative energy. So it's reducing its energy. And then by conservation of energy, the particle that comes out must gain the energy that the black hole lost. So the black hole, basically you extract energy from the black hole by making it eat negative energy. Okay.
Is this related to I'm asking, is this related to the Hawking radiation?
Yes, that's a very interesting question. Yeah, I should have said that, because Hawking radiation is if you ask someone how, like, can black hole emit something? Probably the first answer is, yeah, with Hawking radiation.
Okay.
In fact, so Hawking radiation is a semi-classical process, meaning that the space-time is treated classically, but you put quantum fields on it. So fields are quantized, the space-time is not. While superradiance is fully classical. But superradiance is, in some sense, the classical version of Hawking radiation. Actually, if you read Hawking's original paper, he takes inspiration from superradiance.
Okay.
To derive his famous Hawking radiation. So yes, it is related to Hawking radiation. It's even simpler than that in some sense.
Okay, and that's cool, because so basically these two are the only way that we can understand a black hole to emit something, right?
Yeah, the process of eating a particle with negative energy is also one of the most common explanations for the Hawking radiation. Those are virtual particles, though, so it's harder to understand because fields are quantized, but fundamentally it's the same thing.
Okay.
That Hawking radiation also happens with non-rotating black holes. Okay.
And before let's say slightly changing the matter, I would like to ask you one thing very personal, and I want you to be the most speculative you can be. You're not in any official and formal context, so you can say all the shit all you want. What do you believe? We can find inside black holes?
The point is, we cannot find anything, or we can find something, but we cannot tell the others that stay outside.
Okay, then what do you believe there is that we cannot tell?
Well, the standard picture in general relativity is that black holes are basically empty. There's nothing inside them except at the very center, like at the singularity. Now, the singularity is where classical physics breaks down, and one needs a quantum theory of gravity to explain what happens there, because the gravitational field is so strong that like our theories cannot be applied in that case. So my expectation would be that the classical result, so that the black holes are basically empty, holds true almost everywhere, except that very close to the singularity, you have maybe some other form of matter, some other completely new state of fields or fundamental components of the universe that may no longer be fields at that point, that form something that is not a singularity, but it's something very small but finite. Is
this really what you believe?
Well, believe is a strange word to use for a scientist. This is not what I believe, but what sounds reasonable to me based on my experience in physics.
Okay. I once sorry.
Not very exciting. Maybe you could have expected wormholes or like
no.
Interstellar or whatever. But this is the most reasonable thing to me, at least. Okay.
I once very provocatively, thought, well, what if inside black holes that, such that we cannot see, what if there is God that he made all of these, and he's hiding inside black holes precisely because we cannot see him or her in there. I said, well,
you see, that doesn't work, because God wouldn't be then in causal contact with us. He couldn't do anything to our universe if he was in black holes.
Well, probably he would be God. It would be God if he could be in a black hole and still be in causal contact with us. So, but whatever. Okay, and but you just mentioned a quantum theory of gravity, and now I'm asking you, what do you think? What do you think about? Okay, so basically, you said we have a black hole singularity, and we take general relativity, we apply it there, and it doesn't work. We have infinities pops up. And we take quantum mechanics, which is our greatest achievement of the 20th century. We apply it at the black hole singularity and breaks down. Infinities pops up. So what do you believe quantum gravity, yes, can achieve ultimately? And do you believe, are we, let's say, within a short reach of seeing some major development in quantum gravity and explaining really these fundamentally, I would say, fundamentally radical problems in our understanding of our theories of physics?
So this is a subtle question. I think historically in popular science, this has not been well communicated. Mostly because even in the scientific community, some things were not very clear until about 20 or 30 years ago. The point with quantum gravity is that current theories work fine until you put in them energies extremely high as the so-called Planck scale. Okay, quantum gravity. So there's no problem in quantizing gravity. We can do that as we do that with other fields. The problem is that the problem arises where you ask to this quantum theory of gravity to make predictions at energies above the Planck scale. That doesn't work, okay? But apart from that, we do not need quantum gravity to explain anything, okay? It's not needed to explain anything, away from singularities or stuff like that. And I do not see major developments in the near future because there's basically no way to access that part of the universe experimentally or observationally. It looks like a conspiracy, like the singularities are hidden behind the event horizon. The inflation is hidden behind the basically the fact that inflation washes out everything. So it's extremely hard to access these things observationally, and I do not see that happening in the near future. So quantum gravity is purely speculative. Like the quest for quantum gravity, as I said, is just to formulate a fully consistent and mathematically satisfying theory that includes gravity at any energy. Okay.
Okay. And what do you, okay, then you said that mathematically satisfying, and then I ask you, very briefly, and you can be how critical as you want, what is your take on superstring theory?
Well, I'm not expert on string theory. What do you mean by my take? Like that's
what do you think? What is your opinion? It is just a fancy mathematical construct that theoretical physicists have come up with to solve their, let's say, the problem we have, but we cannot really verify it because it implies much more dimension than what we can actually experience. So it all remains a bit abstract, or may it have some inner, let's say, working within our physical reality?
But the problem with string theory, again, I'm no expert, but as far as I understand, is that it's extremely hard to extract predictions from it. I do not like saying that it's just a beautiful mathematical construction, because historically, seeking simple mathematical constructions proved to work. Many works in physics just pursued mathematical consistency, even mathematical beauty and simplicity in some sense. So string theory is, very interesting and elegant in some ways, but it's extremely hard to make it talk with experiments. That doesn't mean it's not worth to make research on it. But we're not going to need it anytime soon to explain anything in the universe, I think.
Okay. Yeah, I'm reading at the moment the book by Brian Greene, on it's called the Elegant Universe, and he's introducing string theory and some stuff about string, and I can really perceive their I would say enthusiasm about string theory, because they say, look at this new theory, it is mathematically consistent, it combines quantum mechanics with general relativity, it's crazy. Only we cannot test it on the more on the more dimension it predicts, and so you have that. Yeah, god damn it!
The fact that it predicts more dimensions than we observe is not the crucial part, or at least, well, it's part of the problem, but I wouldn't say it's the main thing. It's main reason why it can't be tested experimentally, because that's fine. In some sense, it predicts more dimensions, but then physicists came up with ways to make that compatible with what we see. But this process of compactification is very complicated and has many possible. It can be done in many possible ways, and that's the hard part. It's to me, it doesn't sound unreasonable that there are extra dimensions. Actually, I find the fact that string theory predicts the number of dimensions of space-time extremely elegant and attractive, because it's one parameter less that you have to put in the theory.
Okay.
And the final theory of everything, it would be nice if it didn't have parameters, if it was all obvious, if everything was just the only way it could be.
Yeah, and what about what you just said, the theory of everything? How? Yeah, I'm not gonna ask you if we are short of reaching it, but what do you think? Are we at the point of finding it? I've read some Stephen Hawking's book, and I perceived everyone said he's an incessant quest for the theory of everything, as the last 20 years of research of Einstein. What do you think? Are we in the quest of it?
Well, the answer is pretty much the same as to the previous questions, in some sense. We're doing research, it's purely theoretical, and it's extremely hard. So historically, the research in theoretical physics has been helped a lot by experiments. So advances were much faster when you had experiments to look at, when you had something that suggested you what to do. The problem now is that it's very hard to make experiments that probe, or nearly impossible, that probe the situations where quantum gravity is needed, or the theory of everything is needed. So without all those experiments, we are moving in the dark. Okay. So, I mean, we can surely make theoretical advances, but that cannot be tested. I don't think that can be tested.
Okay. Now I will ask you the last, let's say, speculative question. Sometimes when I think about the cosmos, the universe, black holes, and I mean, pretty much all the exotic objects we have in it, I have the sensation that electromagnetic waves, so what we know as light, from the smallest frequency to the highest frequency, I have them, how do you say them, very in the back of my mind, the hint saying, but this cannot be all. Like electromagnetic waves, surely is almost everything, but it cannot be all, because we can't see everything. And so at this, how do you say, at this turning point, I either have to say, okay, then we will never be able to see what's more, or the other point is, okay, what is the tool, the medium through which I would be able to see more. We would be able to see more, and of course, between the two, I choose to pursue the latter for however nonsense and meaningless it may be, but because I do find it very hard to say, okay, there is a part of the observable universe that we will never be able to see, or there are, yes, there is a part of the observable universe that we cannot reach inside the black hole because electromagnetic waves do not allow it. I find it very, very hard to accept it, and I say there must be something else. What do you think about this?
Well, let me say that electromagnetic waves are not the only way we have to observe the universe. So for every one of the fundamental forces, in principle, we have a way to interact with the universe. One other example is gravitational waves. They are not electromagnetic, and they are carrying a signal full of information to us, which we can detect, just like light. It's just experimentally much more challenging to use them. But in principle, it's a messenger different from light that works just as well. And another one are, for example, neutrinos. Neutrinos interact through the weak force. And we can use, and in fact, we do use neutrinos to study, for example, supernovae. That's not electromagnetic waves. So we do have different signals. The problem with black holes is that it's not just electromagnetic waves that cannot escape the event horizon, but everything. Gravitational waves cannot, neutrinos cannot, electromagnetic waves cannot. Anything that can be described by our accepted theories of quantum fields must behave causally, so must move not faster than the speed of light. And all these things cannot escape a black hole. That's the problem. It's not specifically with light. Saying that light cannot escape a black hole is just a way of saying, if even light cannot, nothing else can.
Okay, but do you believe that's it? We just have to be happy with it, and there will be nothing more. Do you think that our way of seeing, either through electromagnetic waves, as you said, or through gravitational waves, or through neutrinos, all the medium we have at the moment, that's all there is. We will forever be bounded by the speed of light. Because to be honest, if I really if I really ponder over the vastness of the universe, of the cosmos, I do believe the speed of light is quite limiting, for however fast it can be. But I do believe the speed of light is quite limiting. It is giving us. We already know that the real universe is actually much bigger than the observable one. So I say, okay, then we are bounded by the speed of light. We know it is much bigger. Then I can only infer the speed of light is a limit. There must be something else.
That's a good question. I think, classically speaking, that yes, we cannot go light. I cannot make a definite statement about quantum theory of gravity, though. But I don't think that's ever turning into something useful for humans.
Okay. Okay. And then maybe going back to our topic of discussion, I wanted to ask you, what are some challenges that you face in your research area, and also other researchers face, other scientists face in research of black hole superradiance? What are you struggling with?
What do you mean, from a technical perspective? Or,
Yeah, I mean, what obstacles you stumble across, both I would say theoretically, conceptually, and also, maybe they are less interesting, quote unquote, but maybe let's say computationally. Let's put it this way, technically. Yes.
So, yeah, I'm not sure how to answer. So far, I've done mostly research on not superradiance from a theoretical point of view, but the way it changes the dynamics of something, in particular binary systems. So I studied how if you have a binary system and a black hole is undergoing superradiance, then basically there's a cloud forming around it and so on. And I studied how this changes dynamics of binary systems. So the challenge is I'm not sure. Like sometimes it's hard, like the systems are messy and hard. I like personally to do analytical calculations. I like to work with pen and paper whenever possible. This is not always possible, unfortunately. So sometimes I cannot do that. So that's a challenge for me. Yeah, this is it, I guess.
Okay. And what? I think we already mentioned quite some, I would say, limit and challenges that we face with the Lambda CDM model. Do you recall any other, let's say, limit or challenges or difficulties that the Lambda CDM model encounters?
Yeah, okay, good question. So the Lambda CDM model emerged as the standard model of cosmology. But in the past few years, first of all, there's the fact that its two main components, Lambda and CDM, have no fundamental explanation. So that's something to be answered, first of all. But even from a different perspective, even taking those as parameters without looking for a fundamental explanation, in the last few years, a few so-called tensions emerged. So, there's the Hubble parameter, the so-called Hubble parameter that measures the local, how fast the local expansion of the universe is.
With local, what do you mean?
Close to our galaxy.
Okay.
Because if you go too far, then you go too much in the past, and then the universe expanded more rapidly in the past, so it's different.
Okay.
Not more rapidly, but it depends. So I mean, close to us. And so, for example, there are two ways, more than two ways, but the two best ways we have to measure the Hubble parameter are by studying how things close to us move. So they move away from us due to the expansion of the universe. We measure these, and so we compute how fast the universe is expanding. Or we can look at the cosmic microwave background. We can study its anisotropies and fit them with dark matter, dark energy, and so on, and extract what should be the speed of expansion today of the universe. And we find two different numbers. Not too different. Like one is 67, the other is 72 about in the appropriate units. But the fact is that the experimental uncertainties in the last few years reduced a lot. So the two measurements are incompatible with each other. There must be something wrong. We are not sure what that is. I think that could be a hint to go beyond Lambda CDM. So that could be, that's probably an observation that's telling us, look, you need something more refined than the Lambda CDM model now, because that's not able to explain why you get these two different measurements. You need something like some additional components in the universe, some other kind of matter we haven't seen or something like that. And this is the most famous of the cosmological tensions. There are a few more. So I think some cracks are opening in Lambda CDM as observations get better and better with time. I think they can be exploited and used to understand how to go beyond.
Okay. Sorry if I pick you up here, but then what is beyond Lambda CDM? At least what do you not believe? What do you think is beyond Lambda CDM then?
As I said, something like the addition of some extra component in the universe, something like that, or a new parameter, or like something, or even the breaking of one of the assumptions behind Lambda CDM. For example, the fact that the universe is homogeneous and isotropic at large distances. So it doesn't have a preferred direction, for example. maybe these things are only approximately true. So we take them as assumptions in the Lambda CDM, but some of these things may not be exactly true. And so we can find a more general version that reduces to a general model that reduces to the Lambda CDM when these extra components become negligible. This is what I have in mind.
Okay. Hopefully, I will still be alive when some of these advancements.
Same, but I'm optimistic.
Okay.
Optimistic about this kind of advances in cosmology, not so much about particle physics instead.
Why?
Because there's no reason to expect that any crack in the standard model of particle physics could open at the energy scales we can access with new experiments. While there are good reasons to expect to find new physics in cosmology.
Okay. I think I have to leave you, Jimmy. Thanks for this amazing conversation. It was very enticing for me. And I just wanted to say that I will make to pick up very quickly. I will make an episode about string theory and the standard model. So I will cover these topics more in detail, fortunately. And but yeah, absolutely. Thank you very much for being with us. And this was I think we can wrap it up. This was the end of the episode about Lambda CDM and Black Hole Superradiance. So thank you, Jimmy, for being with us. And I hope I will see you maybe to the next Cosmology Journal Club.
My pleasure. Thank you.
Thank you.